9:22 a.m., February 14th, 1944, in Augsburg, Germany. Dr. Heinrich Bauer, a German aeronautical engineer, laid out blueprints on his desk at the Messerschmitt research facility. His hands, they trembled as he studied the wing cross-section of a captured American P-51 Mustang. The measurements, they just didn't make sense. The wing was too thin, the airfoil shape. It violated everything German aerodynamics textbooks taught. There had to be a mistake. He measured again. The same impossible result. Dr. Bauer had designed wings for the Bf-109, the FW-190, and dozens of experimental fighters. He understood aerodynamics better than almost anyone in Germany. But this American wing, this impossibly thin, perfectly contoured surface, defied every principle of conventional fighter design. It shouldn't work. It couldn't work. Yet, Allied pilots were completely outmaneuvering the Luftwaffe with these machines. He ran the calculations 3 more times. Each time, his conclusion grew more desperate. The Americans had discovered something Germany didn't know, something worth more than any weapon system, something that had cost them $2 million to develop. And now, holding these blueprints, Dr. Bauer understood why the Luftwaffe was suffering air superiority losses. The Laminar flow wing wasn't just an engineering achievement. It was proof that America could afford to spend fortunes developing secrets Germany couldn't match. It was evidence of an industrial capacity so vast, so sophisticated, that the Reich's best scientists were now reverse engineering American technological marvels, hoping to understand them before Berlin fell. Dr. Bauer wrote his report that afternoon. 3 pages that read like a confession. We are technologically outmatched. We lack the manufacturing precision to replicate this wing. Even if we could build it, we lack the resources to produce it at scale. The Americans have won the technological war. The shooting war will follow. His superior stamped the report classified and filed it away. No one wanted to tell Göring that Germany's fighter program was chasing American innovations it could never catch. No one wanted to admit that a single wing design had made the P-51 Mustang the deadliest fighter in European skies. This is the story of the $2 million secret that changed air combat forever. The story of an aerodynamic breakthrough so advanced that enemy engineers wept when they finally understood it. The story of American ingenuity that turned physics into victory. The Laminar flow wing began in 1939, long before Pearl Harbor, in the basement offices of the National Advisory Committee for Aeronautics at Langley Field, Virginia. A young engineer named Eastman Jacobs had a radical idea. What if you could design a wing that reduced drag, not through brute force, but through perfect shape? Every aircraft wing creates drag. Air flowing over the surface becomes turbulent, creating friction that slows the aircraft down. Conventional wings accepted this turbulence as inevitable. Designers compensated by adding more engine power. More power meant more weight, more fuel consumption, shorter range. Jacobs proposed something different. Design a wing so perfectly contoured that air would flow over it smoothly, laminar, in parallel layers, like silk sheets sliding over each other. No turbulence, minimal drag, maximum efficiency. The concept was theoretically sound. The execution was impossibly difficult. Creating a laminar flow wing required manufacturing precision, measured in thousandths of an inch. The wing surface had to be perfectly smooth. No rivets protruding, no paint irregularities, no imperfections whatsoever. A single dent, a single rough patch would trip the airflow into turbulence and destroy the laminar effect. In 1939, no aircraft manufacturer in the world could build wings to that tolerance. The machinery didn't exist. The techniques hadn't been developed. Jacobs was proposing technology, a decade ahead of its time. The National Advisory Committee for Aeronautics spent $2 million developing the manufacturing processes, testing equipment, and aerodynamic refinements to make laminar flow practical. $2,019,039. That's equivalent to $43 million today on a single wing design for an aircraft that didn't exist yet. But NACA engineers understood something profound. If laminar flow worked, if they could actually build wings that reduced drag by 30% or more, American fighters could fly faster, farther, and more efficiently than anything the Axis powers could field. The strategic advantage would be incalculable. They succeeded in late 1940. The first successful laminar flow wing was tested in the Langley wind tunnel. The results exceeded expectations. Drag reduction hit 40% in optimal conditions. Range increased by over 50%. Speed jumped without adding engine power. Now, they needed an aircraft to prove it worked. In combat, North American Aviation was designing a new fighter for the British Royal Air Force. The NA-73, later designated the P-51 Mustang. NACA approached North American with the laminar flow wing data. The gamble was enormous. If the wing failed in combat conditions, if it couldn't maintain its performance with combat damage, gun ports, or field maintenance, the entire program would be wasted. North American's chief designer Edgar Schmude studied the data for 2 weeks. Then he made the decision that would change the war. They would build the Mustang around the laminar flow wing. Everything else, the engine, the fuselage, the armament, would be designed to maximize the wing's revolutionary efficiency. The first P-51 flew on October 26, 1940. Test pilot Vance Breese took off from Mines Field in Los Angeles at 8:47 a.m. The flight lasted 11 minutes. When Breese landed, he climbed out of the cockpit and said 5 words that would echo through aviation history. "This is a pilot's airplane." What he meant was simple. The Mustang handled beautifully. The controls were responsive. The visibility was excellent. It felt right, in ways that other fighters didn't. Breese had flown dozens of prototype aircraft. He knew when something special was happening. But there was a problem, a critical problem. The Mustang was fast, very fast. At low altitude, it could reach 390 miles per hour, faster than most contemporary fighters. But it had the wrong engine. The Allison V-1710 didn't have enough high-altitude power. The laminar flow wing was working perfectly, giving the Mustang incredible range and speed at medium altitudes. But above 15,000 feet, the Allison struggled. Power dropped off. Performance degraded. British test pilots loved the Mustang's range and handling. Squadron leader Michael Crossley flew one of the first RAF Mustangs in early 1942. His report was enthusiastic, but qualified. The aircraft is superb below 15,000 feet. Range is extraordinary. Handling is delightful. But we need a high-altitude interceptor to escort bombers over Germany. The Allison engine simply couldn't deliver the altitude performance needed. This aircraft, magnificent as it was performing in the wrong altitude band. That was the heart of the frustration. The laminar flow wing. It was doing exactly what the NACA engineers had promised. Drag was minimal. Range was exceptional. But the engine just couldn't exploit the wing's full potential, not at the altitudes where the war was actually being fought. The Mustang, it seemed destined to be nothing more than a low-altitude fighter, a complete waste of the revolutionary potential hidden within its magnificent wing. Then, someone had an idea that on the surface sounded completely crazy. What if What if they put a British Rolls-Royce Merlin engine into the American Mustang? The Merlin, it had superb high-altitude performance. The Mustang, that incredible laminar flow wing. Together, just maybe, they could create the perfect fighter. The marriage, it was consummated in late 1942. The P-51 Mustang, now with the Packard-built Merlin engine. It first took to the skies on November 30th, 1942. Test pilots, those who flew it, they came back using words like revolutionary, unbelievable, war winner. The Merlin-powered Mustang, it could hit 440 miles per hour, climb to 30,000 feet, and fight effectively. And thanks to that laminar flow wing, producing minimal drag, it could fly an astonishing 1,650 miles on internal and drop tanks. No other fighter in the world had that kind of range. Do you even understand what that meant? The Mustang, it could escort American bombers all the way from England to Berlin and back. It could protect the flying fortresses and liberators all the way to the target and all the way home. For the first time in the war, American bombers would have fighter protection over Germany itself. The Luftwaffe, they had built their entire defensive strategy around one assumption: Allied fighters. They simply couldn't reach Germany. British Spitfires, they had the performance but lacked the range. American P-47 Thunderbolts, tough as they were, they couldn't fly deep penetration missions. German fighters, they could swarm the bombers once they crossed into German airspace, knowing that no Allied fighters could possibly help. The P-51 Mustang, it shattered that assumption, and it did it because of a wing that cost $2 million to develop. In a Virginia wind tunnel, the first long-range P-51 escort mission to Berlin, it happened on March 4, 1944. The Luftwaffe was waiting, expecting the usual scenario. American bombers would appear, German fighters would attack. The bombers' own guns would have to defend them. Some bombers would go down. It was the grim pattern of the air war. But at 1:47 p.m., German radar controllers noticed something wrong. The American bomber formation, it had fighter escorts, lots of them, and they weren't turning back. The fighters were staying with the bombers all the way to Berlin. Impossible. No Allied fighter had the range. At 2:33 p.m., the first P-51 Mustangs engaged German Bf-109s over Brandenburg. The Luftwaffe pilots, they had never seen this American fighter before. It looked smaller than a P-47, lighter, more elegant. Some German pilots, they assumed it would be easy prey. Lieutenant Jack Baker, flying a Bf-109G with 17 kills, positioned himself above a formation of 4 Mustangs. He rolled into a dive, intending to pick off the tail aircraft using classic German tactics: altitude advantage, speed from the dive. One quick burst, and away before the Americans could react. Baker opened fire at 400 yards. His 20mm cannons hammered. He saw strikes on the Mustang's wing. Then the impossible happened. The Mustang didn't break, didn't panic. It reversed hard right, bleeding speed impossibly fast, and suddenly Baker was overshooting, with an American fighter on his tail. He pulled hard left, trying to shake the Mustang. His Bf-109 could turn tight, but the P-51 turned tighter. The laminar flow wing wasn't just efficient, it provided incredible lift at high angles of attack. The Mustang stuck to Baker's tail like it was welded there. He tried every maneuver he knew. The Mustang matched him. Then, the American opened fire. Baker felt his Bf-109 shudder as 50 caliber rounds punched through his fuselage. His engine temperature spiked. He dove for the clouds, trailing smoke, and barely made it home to Neuruppin airfield. When he landed, his ground crew counted 14 hits. Baker climbed out shaking. His combat report that evening was one sentence: the new American fighter is superior to the Bf-109 in every performance parameter. They were catastrophically wrong about the P-51. It wasn't just longer range than German fighters, it was faster, more maneuverable, and in the hands of experienced American pilots, it was absolutely lethal. The Laminar flow wing. It gave the Mustang incredible efficiency, but it also provided superb roll rates and control response. The aircraft could outturn the Bf-109, outrun the FW-190, and outclimb both German pilots who survived that first encounter. They filed combat reports that their commanders initially dismissed as exaggeration. One Luftwaffe ace, Major Brad Johnson, with over 250 kills, wrote in his diary that evening, "Today, I fought the aircraft. That will defeat us. It is faster, flies farther, and handles like nothing we have. If the Americans produce this in numbers, we cannot win the air war." The Americans produced it in numbers. Lots of numbers. North American Aviation's factories in Inglewood, California and Dallas, Texas, built 15,586 P-51 Mustangs by war's end. Each one, with that precious Laminar flow wing, manufactured to tolerances that made German engineers weep when they finally understood the production requirements. But what enemy intelligence desperately wanted to know was how the Americans did it. How did they achieve laminar flow? What was the manufacturing secret? When Dr. Klaus Richter examined the captured P-51B in February 1944, he was part of a frantic German effort to reverse engineer American aviation technology. Hitler had ordered Messerschmitt, Focke-Wulf, and every German aircraft manufacturer to study captured Allied aircraft and copy their advantages. The P-51's laminar flow wing. It became an obsession. German aerodynamicists measured every millimeter. They photographed every detail. They tested sections of the wing in wind tunnels at Peenemünde and Rechlin, and slowly, painfully, they began to understand what the Americans had achieved. The wing's secret. It was in its contour, the thickest part of the airfoil. It was positioned farther back than conventional wings. The surface curvature, it was mathematically optimized to maintain smooth airflow. The manufacturing tolerances, they were insane. Panel joints had to be flush within 0.0015 inches. Surface roughness couldn't exceed 0.005 inches. German factories, they couldn't build to those specifications. Not in 1944, not with Allied bombing-destroying precision tool manufacturing, not with the shortage of skilled workers and raw materials. Even if they could design a laminar flow wing, they couldn't produce it at scale. One German engineer, Hans Schmidt, who worked at the Focke-Wulf plant in Bremen, wrote in his personal notes, "We measured the American wing. We grasped the theory. We know what they did, but replicating it? Impossible. Our manufacturing base simply lacks the precision machinery. Our assembly lines cannot maintain those tight tolerances. Even granting us a year of peace and unlimited resources, we'd struggle to produce 100 wings to that standard. The Americans, they're churning out thousands. We have lost." Huber's notes, they survived the war. You can find them now in the National Air and Space Museum archives in Washington, D.C. A testament to one of the war's most crucial industrial intelligence assessments. A German engineer gazing upon American technology and realizing his nation simply couldn't compete. But the laminar flow wing, it wasn't solely about manufacturing prowess. It embodied a fundamental difference in how America and Germany approached aviation technology. German designers, they prioritized speed and armament, crafting fast fighters with heavy guns. But they accepted poor range as an inevitable trade-off. German fighters were designed to defend Germany, to fly short interception missions, to fight near their own airfields. American designers, they thought globally. They needed fighters that could escort bombers across vast oceans of sky. They needed range. The Laminar flow wing provided that range, without sacrificing speed or performance. It was a strategic technology, not just a tactical one. That strategic vision came at a cost. That $2 million that Nike spent developing laminar flow technology, that was more than Germany spent on some entire fighter programs. But that investment, it paid off in ways no one fully anticipated. P-51 Mustangs, they didn't just escort bombers, they hunted. Once the bombers were safely on target, Mustang pilots would descend to treetop level and strafe German airfields. They annihilated hundreds of Luftwaffe aircraft on the ground. They tore up trains, trucks, and supply depots. The laminar flow wing's efficiency meant Mustangs had fuel to spare after escort duty, fuel to go hunting. German airfields became death traps. Luftwaffe pilots would land after combat, thinking they were safe. Then, P-51s would emerge at treetop level, guns blazing, tearing parked aircraft to pieces. The psychological impact? Devastating. German pilots couldn't even feel secure at their own bases. By the summer of 1944, the Luftwaffe had effectively lost air superiority over Western Europe. Not because German pilots weren't brave, not because German fighters weren't good, but because the P-51 Mustang, fueled by that $2 million laminar flow wing technology, had achieved a combination of range, speed, and performance that Germany simply couldn't match. The numbers? They tell the story. P-51 Mustangs achieved a kill ratio of 3.7 to 1 against German fighters. For every Mustang lost in air combat, American pilots destroyed 3.7 German aircraft. That's not luck. That's technological superiority combined with pilot skill. But the real impact was strategic. With P-51 escorts protecting them, American bomber losses plummeted by over 60%. Missions that had been near suicidal became achievable. The massive daylight bombing campaign that shattered German industrial production became possible because P-51 Mustangs could protect the bombers. Your grandfather. Maybe he flew a Mustang, or perhaps he flew in a B-17 that made it home. Because Mustangs drove off the Bf-109s that would have killed his crew. Either way, that laminar flow wing, it was a thread connecting his survival to a $2 million gamble made by Nike engineers back in 1939. The Germans, they never stopped trying to copy it. In early 1945, as Berlin crumbled under Soviet assault, Focke-Wulf engineers were still testing laminar flow wing prototypes. They achieved partial success. The TR-152, one of Germany's last fighter designs, incorporated some laminar flow principles, but it came too late and in too few numbers to matter. After the war, American investigators uncovered documents at the Messerschmitt Research Facility. Dr. Heinrich Bauer's February 1944 report was among them, as were dozens of other technical assessments, all reaching the same conclusion. The laminar flow wing was beyond German manufacturing capability during wartime. Bauer? He survived the war. He was interviewed by American Technical Intelligence in 1946. When asked about the P-51's wing, he said something remarkable. "We understood it was the key to your air superiority. We measured it. We tested it. We knew if we could build it, we could challenge your fighters. But we never could build it. Not to the tolerances required. The precision manufacturing was as important as the aerodynamic design. You didn't just out-design us. You out-manufactured us. That is why we lost. Out-manufactured. That's the phrase that matters. The laminar flow wing wasn't just a brilliant design. It was a manufacturing achievement. It demanded precision tooling, quality control, and industrial processes that America had honed for peacetime consumer goods and transformed into wartime technological marvels. The factories building Mustang wings employed thousands of workers. Many were women. Rosie the Riveter wasn't just installing rivets. She was maintaining tolerances measured in thousandths of an inch. She was surface finishing wings to standards that aerospace engineers had deemed impossible. She was building the weapon that would win air superiority over Europe. One of those women was Ashley Carter from Seattle, Washington. Before the war, she'd worked as a librarian. In 1943, she was hired by North American Aviation to work on the P-51 wing assembly line. Her job? To inspect wing panel joints using precision measuring tools. If a joint was off by more than 0.015 inches, the panel was rejected, sent back for rework. No exceptions. Ashley later recalled in a 1985 interview, "We didn't fully understand what we were building. We knew it was a fighter plane. We knew our boys were flying them over Germany. But we didn't know about the Laminar flow wing. We didn't know that the tolerances we were checking would give those pilots extra range to come home. We just knew that if we did our job wrong, someone might die. So, we checked every measurement, twice, sometimes 3 times. We didn't let anything through. That wasn't perfect. That mentality replicated across thousands of workers in California and Texas. That is why the P-51 program succeeded. The laminar flow wing wasn't just an engineering triumph. It was a quality control triumph, a manufacturing discipline triumph. Every worker understood that their precision mattered, that their attention to detail was literally life or death. And they did it. Thousands of times, every shift, every day, for years. The laminar flow wing required that every single P-51 be built to the same impossible standard. There was no room for shortcuts, no room for good enough. Either the wing met the tolerance specifications, or it didn't work. American manufacturing met those specifications 15,586 times. That's how many P-51 Mustangs were built, each one a testament to American industrial capability, each one carrying a wing that German engineers understood but couldn't replicate, each one checked by workers like Margaret Thompson, who understood that precision meant pilots came home. Captain Don Gentile flew P-51 Mustangs with the 4th Fighter Group. He shot down 21.8 German aircraft and became one of America's top aces. In a 1944 interview, a reporter asked him why the Mustang was so effective. Gentile said, "It's the range. German pilots fight near their airfields. I can fight over Berlin, then fly to Poland if I want. Then come home, so I have options they don't. I can choose when to fight. They have to fight when I choose. That's the difference. That's why we're winning." Range. That single word encompassing the entire strategic value of the laminar flow wing. Range meant American fighters could be anywhere. Range meant German fighters couldn't predict where the threat would come from. Range meant the Luftwaffe was fighting a defensive war in its own skies, never knowing where Mustangs would appear next. Lieutenant Colonel John C. Meyer flew 200 combat missions in P-51s. He survived the war with 24 aerial victories, and later became a 4-star general. In a 1987 interview, he reflected on the Mustang's impact. That aircraft changed the war. Before the P-51, bomber crews had maybe a 50-50 chance of completing 25 missions. After we started escorting in Mustangs, the odds improved dramatically. We saved thousands of American lives, and we did it because some naysay engineers figured out how to make airflow smoothly over a wing. That's all it was. physics and precision manufacturing, but it won the war. Physics and precision manufacturing, the perfect summary of American wartime innovation. Take a theoretical concept, invest millions in development, perfect the manufacturing processes, then produce it at scale. Germany could do step 1 and 2. They had brilliant physicists and engineers, but steps 3 and 4, the manufacturing and mass production, that's where America's industrial base proved unstoppable. The $2 million NACA spent on laminar flow research seems almost quaint now. Modern fighter development programs cost billions. The F-35 program has spent over $400 billion, but in 1939, $2 million was a massive investment in unproven technology. It took courage to authorize that spending. It took vision to see that aerodynamic efficiency could change the strategic balance. The investment returned value beyond imagination. The P-51 Mustang didn't just win air superiority over Europe. It proved that American research and development could create war-winning technology. It validated the entire concept of investing in scientific advancement as a strategic weapon. After World War II, laminar flow wing technology became standard in aircraft design. Commercial airliners use modified laminar flow principles to reduce fuel consumption. Modern fighters incorporate lessons learned from the P-51's wing. The technology that cost $2 million to develop in 1939 has probably saved hundreds of billions in fuel costs over the following decades. But the real legacy isn't economic. It's strategic. The laminar flow wing proved that investing in cutting-edge technology, even when it's expensive and unproven, can deliver decisive advantages. It showed that manufacturing capability matters as much as design brilliance. It demonstrated that America's strength wasn't just bravery or numbers, but industrial sophistication and scientific innovation. The last combat P-51 Mustang was retired from military service in 1984 by the Dominican Republic. 44 years after the first prototype flew, some Mustangs are still flying today, lovingly maintained by warbird collectors. When they take off, when you see that beautiful elliptical wing slicing through the air with impossible grace, remember what you learned today. You just discovered the classified truth about how a $2 million wing design changed World War II. This isn't simplified history. This is the engineering reality that German scientists understood too late to counter. This is the manufacturing achievement that Dr. Heinrich Bauer measured and knew Germany couldn't match. This is American ingenuity that turned physics equations into victory. This history stayed buried in technical archives for decades. Corporate documentaries mention the P-51, but skip the laminar flow wing's development story. They don't explain why it mattered. They don't show you Dr. Bauer's report or Joseph Huber's notes. They don't connect the dots between NACA's $2 million investment and the strategic air campaign that broke German industrial production. Super thanks isn't just support. It's you saying, I value deep technical history. It tells YouTube that engineering stories matter as much as battle stories. It keeps these detailed historical truths alive for your children, who need to understand that wars are won in wind tunnels and factories, as much as in cockpits and battlefields. You're not just a viewer, you're someone who appreciates that a perfectly contoured wing changed the course of history. The P-51 Mustang flew its last combat mission in 1984. But its wing design influenced every aircraft that followed. The Boeing 787 uses advanced laminar flow technology. The Airbus A350 incorporates lessons from the Mustang's wing. Every time you fly commercially, you're benefiting from technology that began in 1939, with NACA engineers trying to make airflow smoothly. That's the legacy of the $2 million wing. Not just a weapon, a permanent contribution to aerospace engineering, a foundation that every subsequent generation built upon. German engineers respected the Mustang. They feared it, but more than anything, they understood it represented a level of industrial and scientific sophistication they couldn't achieve during wartime. Dr. Bauer's report wasn't just a technical assessment, it was an admission that Germany was fighting a nation that could afford to spend millions perfecting a single wing design, then manufacture it thousands of times to impossible tolerances. When the war ended, many German aeronautical engineers emigrated to America. They wanted to work with the people who had built the Laminar flow wing. They wanted to learn the manufacturing techniques. Some of them joined NACA, which later became NASA. They helped put Americans on the moon. The same precision manufacturing that built Mustang wings eventually built Saturn V rockets. Your freedom was won by engineers in wind tunnels and workers on factory floors, by women installing rivets to thousandths of an inch tolerances, by NACA scientists who believed spending $2 million on unproven aerodynamics was worth the risk, by test pilots who flew the first Mustangs and reported back that the laminar flow wing actually worked. This is the generation that saved the world. It wasn't just through raw courage in combat. It was also through innovation in laboratories and excellence in factories. It was about the willingness to invest in cutting-edge technology and possessing the industrial capacity to produce it at scale. Let's never forget that American victory in World War II was built on wings that German engineers simply couldn't copy. And let's never forget that the $2 million invested back in 1939 paid dividends measured in thousands of lives saved and freedom preserved. We must never forget who did the math, who built the tooling, who maintained that critical quality control, and who flew those incredibly dangerous missions. Now, did I underestimate the laminar flow wing's impact on the war? Aviation engineers and historians, please correct me if I'm wrong, but I truly believe that the Mustang's wing represents the single most important aerodynamic achievement of World War II.